This is very exciting, my first A-level paper. This is the Edexcel 2018 Paper 1 walkthrough. I hope you enjoy it. Starting with question number 1, so this is simplifying an expression with the small angles. We can approximate cosine and sine as polynomials. Sine of 3 theta is very close to 3 theta when theta is small, and cos of 4 theta is very close to 1 minus 4 theta squared all over 2. And so it allows us to write this particular fraction as 1 subtract and then 1 minus 4 theta squared over 2 all over 2 theta times 3 theta. All that remains is for us to simplify that down. The numerator simplifies to 8 theta squared. The denominator to 6 theta squared, and the whole fraction therefore simplifies to 4/3. 3 nice marks. Question number 2 is a test of your differentiation skills. So the first step will be to turn the equation into something that is differentiable. We want to write these as a constant multiple of a power of x, and so that means changing the 24 root x to a 24x to the half. Then we can apply the standard rules for differentiating a polynomial. Times by the power, subtract 1 from the power. X squared differentiates to 2x. Minus 2x differentiates to minus 2, and multiplying by a half takes the 24 to 12, and subtract 1 from a half, you get negative a half. So 2x minus 2 minus 12x to the minus a half. If you wrote the minus 12x to the minus a half as minus 12 over x to the half, or minus 12 over root x, that's absolutely fine. Second differential, differentiate again, 2 plus 6x to the minus 3 over 2. Negative a half times negative 12 is plus 6. Subtract 1 from negative a half, you get negative 3 over 2. For b, we want to verify that there's a stationary point when x equals 4. That means substituting 4 into our expression for the differential. You can see a clear substitution there. 2 lots of 4, subtract the 2 that's already there, subtract 12 lots of 4 to the negative a half. All of that boils down to 0. And the point of that is that we have verified that we have indeed got a stationary point. For C, to determine the nature of the stationary point, I'm going to apply the second derivative test. The second derivative test says that if the second derivative is positive, it's a minimum. If it's negative, it's a maximum. And if it's 0, we're not quite sure. We can't reach any conclusions other than we're dealing with a point of inflection. When we plug 2 into the second differential, we get 2.75 out. And the interesting thing about 2.75 here is that it is greater than 0. And that tells us that our point is a minimum point. Question number 3. So this is to do with our formula for sectors using radians. So theta over 2r squared will give me the area of a sector. It tells us in the question that that is 11, so I can equate theta over 2r squared to 11. With the perimeter of the shape, well, we're going to have 2 radii, add together the arc length a to b. The arc length is theta r, so we'll get theta r plus 2 lots of the radius is going to be 4 lots of theta r. It's 4 times the length of the arc. And we can simplify and solve the equation to get theta equals 2/3. We can take our 2/3 and substitute it into the first equation. So 2/3 over 2 times r squared is 11. Therefore r squared is equal to 33. R is equal to root 33, which does not simplify. For question 4, the iterative formulae. I'm going to take the equation that we're given and replace the y with x, because y is equal to x. Essentially, we're solving 2 ln of 8 minus x is equal to x. I'm going to bring the x onto the left-hand side, so 2 ln 8 minus x is equal to 0. The point of doing this is it allows me to use the change of signs argument along with continuity. So when we plug the two values 3 and 4 into this equation, we'll get one positive and one negative. Plugging x equals 3 comes out as 0.22, which is positive. Then when x is 4, we can plug that in and we'll get negative 1.23, which is negative. And because we have gone from a positive at 3 to a negative at negative 4, and because we know this particular function is continuous, the ln function is continuous, x is continuous, so the subtraction of the two components will be continuous too. Essentially, that line between the two values must cross the x-axis somewhere, and that tells us that there must be a root that lies between the two values, between 3 and 4. For part B, we've got to decide if it's going to work or not, essentially as an iterative formula. So I'm going to draw in values, we plug 4 in, and each time we get an output, we plug that output back in, and we get the cobweb shape diagram that's on the screen there, as it cobwebs inwards or spirals inwards towards the solution. So the answer to this question is yes, it will work. If it were a different graph, it might spiral outwards and would diverge away from the solution and therefore not give us any, but this one converges towards the solution, and so yes, we can use the iterative formula to find the solution. Okay, question number 5. We're given a fraction, trigonometric fraction, and we need to differentiate it. Differentiating a fraction composed of two different functions is giving us a big hint towards using the quotient rule for differentiating. So with the quotient rule, we assign the numerator to be our u and the denominator to be our v. And then I'll do a little helpful differentiating of u and v before jumping into the quotient rule. So 3 sine theta will differentiate to 3 cos theta, and 2 sine theta plus 2 cos theta will differentiate to 2 cos theta subtract 2 sine theta. And then we can plow into the quotient rule itself, v du dx minus u dv dx all over v squared. And so it's a case of just being careful with each step that you do. And the more observant amongst you will notice I forgot to close a bracket there after the 2 cos theta, which is disappointing, I know. And we have v du dx minus u dv dx, and all of that's going to go over v squared. And substituting in v squared, we get 2 sine theta plus 2 cos theta all squared. Now I'm going to expand out everything and simplify where I can. So the first expansion, 3 cos theta times 2 sine theta is 6 cos theta sine theta. Then we've got 3 cos theta times 2 cos theta, gives me 6 cos squared theta. Then we've got minus 3 sine theta times 2 cos theta is minus 6 cos theta sine theta. And lastly, minus 3 sine theta times minus 2 sine theta is plus sine squared theta. The denominator, expand out the 2 sine theta plus 2 cos theta squared is going to give us 4 sine squared theta plus 8 sine theta cos theta. Plus 4 cos squared theta. Okay, for the next line, just looking at that fraction, seeing what's going to cancel, we've got a 6 cos theta sine theta minus 6 cos theta sine theta. We're cancelling the numerator, leaving us with 6 lots of cos squared theta and 6 lots of sine squared theta. I'm going to immediately factorise the 6 out, giving me 6 lots of cos squared theta plus sine squared theta. That will simplify to 1 next. Then the denominator, we've got 4 lots of the sine squared theta plus cos squared theta. You may be able to see where that's going now. Plus, and then using the double angle formula for sine 2 theta, we can see we've got 4 lots of 2 sine theta cos theta, which we'll reduce in a second. The numerator simplifies to 6, cos squared theta plus sine squared theta equals 1. Similarly, the cos squared theta plus sine squared theta equaling 1 on the denominator leaves us with 4 plus 4 sine 2 theta. And lastly, divide the top and the bottom by 4. We'll get 6 over 4 or 3 over 2 if you simplify, all over 1 plus sine 2 theta, which is what the question wanted in this case. Capital A is 3 over 2. Well done if you got that one. Question 6. This is a coordinate geometry question. So first of all, we want to find the line P to A. Well, we know that the line P to A is going to be perpendicular to the line L. So the first thing I'm going to do is notice that the gradient of the line L is 2. Therefore, the gradient of our line P to A, passing through P to A, is going to be negative a half. It's the negative reciprocal of 2. Then plugging it into y minus y1 equals mx minus x1, we'll get y minus 5 equals negative a half, lots of x minus 7. I'm going to get rid of the negative a half by multiplying by 2. So 2y minus 10 on the left, minus x, be careful, plus 7 at the end. And then bring the x onto the left, so bring the negative 10 onto the right, we'll get 2y plus x equals 17, which is what the question wanted. For B, to work out the equation of the circle, well, we're given the coordinates of A, the centre of the circle, so we know those already. We want to work out the coordinates of P, so I'm going to solve the 2 lines we have, the line passing through PA and the line L simultaneously. Any number of correct ways of doing it. If you end up with x equals 3 and y equals 7, then you've carried that out correctly. And so the point P is 3, 7. That allows us to find the length of A to P, or if you prefer, the radius of the circle. So plug the points A and P into the distance between 2 points formula. Essentially, it's just Pythagoras. Difference between the x's squared, the difference between the y's squared, and then square root those, you get the square root of 20. You could simplify that if you want to 2 root 5. I haven't here because we're about to square it in a second anyway. And so the equation for C, x minus a squared plus y minus b squared equals r squared for any circles. So in this case, x minus 7 squared plus y minus 5 squared equals 20. Square root of 20 squared is, of course, 20. For C, to find the value of the constant k, well, we know the line is parallel to L, so essentially we're drawing another line parallel to L on the opposite side of the circle. It's going to meet the circle at the point that would make the diameter from P to this new point at the diameter of the circle. So essentially if we take the vector that takes us from P to A and then apply that vector to A, it would take us from A to the point where the line meets the circle on the opposite side. So P to A is 4, negative 2. And then if we add 4, negative 2 to A, we'll get 11 over 3. And so we know this line passes through 11 over 3, so I'm substituting that in. Solve it to find K is negative 19, and that's our equation. Question 7, the integration question. So for the first one, it tells us that K is a positive integer. We need to integrate between K and 3K, 2 lots of 3x minus K. To show this clearly, I'm factorising 2/3 out of the integral, essentially changes the numerator from 2 to 3. The advantage of doing that means that the numerator is now the exact differential of the denominator, and so we can apply integration by inspection. If you attempt to do a substitution here, that will work as well. It'll take you slightly longer to carry out the substitution and then reverse it, but you'll end up in the same place. I haven't done that. I've just factorised out 2/3. The top's the differential at the bottom, so we've got 2/3 on the outside, and then ln of the denominator, ln of 3x minus k, and we're integrating that between k and 3k, so we can substitute 3k in, and then we can substitute k in and subtract the second from the former. Substituting 3k in, 3 lots of 3k is 9k, 9k minus k is 8k, you can see there, and the same with the k, we're going to get 3k minus k, which is just 2k. So 2/3 of all of that. Applying the laws of logarithms, when we're subtracting a logarithm from another logarithm, we can divide what's on the inside, so it will be 8k over 2k inside the log, and so 2/3 ln of 4 when that boils down, and the point is that that value is independent of the value of k that was chosen at the very start. That is an exact area. You can change k, but it won't change the area. For b, we're now integrating between k and 2k. We've squared the denominator, which definitely changes the nature of this integral. This is no longer going to be a natural log. The top's not going to be the differential of the bottom. However, we can rewrite this integral as 2 lots of 2x minus k to the power of negative 2. And this is something we can just integrate without any further changes. So we're adding 1 to the power, adding 1 to the minus 2. We're dividing by the differential, we're dividing by 2, and that cancels with the 2 that's out the front. And also dividing by the negative 2 gives us a negative at the front. Sorry, dividing by the negative 1 gives us a negative at the front. And our integral is minus 2x minus k all to the power of negative 1. Integrating that between 2k and k. So plug 2k in first of all, and then plug k in second. And we get an expression that can be simplified down quite nicely. There's a few ways of sort of simplifying the expression from here. I've decided to write these as fractions and get a common denominator. So minus 1 over 3k minus 1 over k. If you've cancelled the negatives already, that's obviously absolutely fine. That's going to be negative 1 over 3k plus 3 over 3k. And then, because this is the show that question, I've gone even further. 2 over 3k, and therefore is 2 over 3 all over k. The advantage of writing it like that is we can quite clearly see that we're dividing by k here. We've got a constant divided by k, and that's the structure of an inversely proportional relationship. So the area is inversely proportional to k, which is what the question's asked us to show. All right, question number 8. So we've got a sinusoidal model here measuring the depth of water. Okay, so to find the depth of the water in the harbour when the boat enters, well, it enters at 6:30 a.m, so t is 6.5. So plug 6.5 into the equation for the depth. Plug that into your calculator. Make sure you're in degrees and not in radians. It comes out as 4.48 meters. Okay, for B, we want the depth to be at least 3.8 meters, so I'm going to substitute D for 3.8 and solve the equation. To solve that equation, I'm subtracting 5 from both sides, then dividing both sides by 2. And then lastly, doing inverse sine of negative 0.6 gives me my first solution, which is negative 36.87. However, we want the other solutions that are positive, so we can do a mixture of things. We can subtract negative 36.87 from 180 to get 216.87, or we can add 360 to get 323.13, or any other method that you use that is correct to solve trig equations. As long as it's a legitimate method that you've used correctly, you'll get exactly the same values as I've got there. Divide them all by 30. And the one we want will give us 10.77. When you change 0.77 from a fraction over 100 into a fraction over 60, you get 46. So 10:46 a.m. for that one. All right, question number 9. We've got an interesting looking curve. X squared minus 2xy plus 3y squared equals 50. We're going to differentiate this. This is implicit differentiation. Differentiating x squared, you get 2x. Differentiating minus 2xy using the product rule, we'll get minus 2y minus 2x lots of dy by dx. And differentiating 3y squared gives us 6y lots of dy by dx will be equal to 0. 50 differentiates to 0, it's constant. On the next line, I'm going to factorize out the factors of dy by dx. So we've got a 6y and a minus 2x, and we're going to do 6y minus 2x lots of dy by dx. I'm going to bring the 2y and the 2x onto the right-hand side. And then if we divide both sides by 6y minus 2x, we can actually factorize that straight away. I'm going to factorize the numerator. You didn't have to factorize before cancelling these 2's. You can cancel them later, that's absolutely fine as well. But we get y minus x over 3y minus x, which is what the question wanted. For B, finding the exact coordinates of P. Well, we know the gradient's undefined at this point P because it's got a vertical tangent going up there. So that's going to happen when the denominator is 0 in our differential. So I take the denominator, the 3y minus x bit, I force it to equal 0, move the x onto the right hand side, 3y equals x. We can substitute that into the original equation of the curve. Gives us 3y all squared minus 2 lots of 3y times y plus 3y squared will be equal to 50. And this generates a quadratic equation we can solve to find the values of y. for this particular point P. We're going to get one positive and one negative. The positive one is going to be actually point Q, but we're not interested in that one. We're only interested in point P. So when I go about solving this this quadratic, it simplifies down quite nicely. You can solve it in any number of ways. A correct way will lead you to the solutions y equals plus or minus 5 over root 3. I've rationalised the denominator on that to tidy it up. So multiplying the numerator and the denominator by root 3, which gives me plus or minus 5 root 3 over 3. We know the positive one is the point Q, and so the negative one, well, we know that x is equal to 3y from earlier on, so x must be equal to plus or minus 5 root 3 over 3 times 3, or if you prefer, plus or minus 5 root 3. So x equals minus 5 root 3, y equals minus 5 root 3 over 3, and those are the coordinates of my point P. For part C, it asks us to explain how we would find the coordinates of the point furthest north from the origin rather than do it. Well, to do that, we'd need to solve simultaneously the equations y equals x and x squared minus 2xy plus 3y squared equals 50, and then find the solution that is in the top right quadrant of the graph, the positive solutions, if you prefer. You do that and you'll be able to find the point that they are asking for. Okay, for question 10, it gives us a differential equation. And so for part A, essentially we're just solving the differential equation dh by dt equals h cos of 0.25t all over 40. To solve these, I'm going to separate the variables, separate the h's onto the left-hand side and leave the t part onto the right-hand side. So to do that, I'm going to divide both sides by h. So on the left-hand side, we'll have a 1 over h, and on the right-hand side, we'll have 1/40th of cos 0.25t. You can take the 1/40th outside the integral if you prefer. And then I'm going to separate the dh and the dt. The purists amongst you will disapprove. You can't treat dh by dt like a fraction, and of course you're absolutely right. However, for the purposes of displaying a neatly elegant solution, it makes sense to do that. The integral of 1 over h is ln h. The integral of 1/40th cos of 0.25t is 1/10th sine 0.25t, plus the constant of integration plus c at the end. Now it gives us some initial information. It tells us that t is 0 when h is 5. So I'm going to plug those in. Ln of 5 will be equal to c, because sine of 0 is 0. And so c will be ln 5. Going back to our formula, plugging c to be ln 5 in, we'll get ln h equals 1/10th sine of 0.25t plus ln 5. And all that remains is for us to tidy that up. So I'll raise both sides of the equation to the power of e. I'm going to separate the right-hand side of this, so I'm going to split the two parts raised to the power of e into two separate parts. So we'll get e to the ln 5 times by e to the 0.1 sine of 0.25t. And the point of doing that is that the e to the power of ln 5e and ln are inverse functions. So they will, if you like, cancel each other out, leaving us with 5 e to the 0.1 sine 0.25t, which is what the question wanted us to show. For B, we're going to get a maximum height when sine of 0.25t is equal to 1. That's the largest value that sine can take. And so we can substitute sine of 0.25t for 1, plug that in to get the height, which will be 5 times e to the 0.1. Plug that into your calculator, 5.53 meters. And then for C, well, the next time that's going to happen is at 5 over 2 pi, following the sinusoidal pattern. And so if we solve 0.25 equals 5 over 2 pi, we get t to be 31.4 seconds. All right, question number 11. It's quite a tricky binomial expansions question. We've got actually quite a few steps to go through here. First thing I'm going to do is I'm going to take the square root of the fraction that they've given us. I'm going to rewrite it into two separate brackets that we can expand. So we've got 1 plus 4x to the half. That's just the square root of the numerator. And then the 1 minus x in the denominator, we can rewrite that as 1 minus x to the power of negative a half. And then dealing with each one of those one at a time, I'll do the 1 plus 4x to the power of a half first, and using the formula for the binomial series expansion, plugging the numbers in, we get 1 plus 0.5 times 4x plus 0.5 times negative 0.5 over 2 lots of 4x squared. We could continue going, however, in the question we can see it only goes up to the power of x squared, so anything larger than that's not going to be relevant to us, so I'll just put a plus dot 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 and leave that there. Simplifying each part of that, we get 1 plus 2x minus 2x squared. You can do that on a calculator if you want to. For the 1 minus x to the power of negative a half, we'll get 1 plus negative 0.5 times negative x plus negative 0.5 times negative 1.5 all over 2 times by negative x squared. Brackets are really useful when doing binomial expansions, especially when you have so many negatives going on. And if you carefully simplify that, you'll end up with 1 plus 0.5x plus 0.375x squared. If you've done those as fractions, it's absolutely fine. Okay, next we want to multiply our two expansions together. So 1 plus 2x minus 2x squared multiplied by 1 plus 0.5x plus 0.375x squared. And again, when carrying out this expansion, there's a lot of parts of it which will end up with powers of x that are larger than 2. So I'm just going to ignore all of those and just multiply the 1 by all of the parts on the right. I switched to fractions here just to make it look a little bit tidier. And then the 2x by just the first two, and then the 2x squared just by the first one. But any order that simplifies eventually to 1 plus 5 over 2x minus 5/8 x squared is correct, and that's what the question wanted us to show. Both expansions will be valid when the modulus of the coefficient times x is less than 1. So for the right hand one, that's just going to be when x is less than 1, but we also need it to be true for both. So I'm going to look at the one where 4x, modulo 4x has to be less than 1. That gives me modulo x being less than a quarter. And obviously if it's less than a quarter, it's going to be less than 1, so it's going to work for both expansions. For C, it asks us to plug in 1/11 into our fraction and square root it, and also plug it into the expansion and equate the two to come up with an approximation for root 6. So I shall plug 1/11 into the fraction first. and that's going to be approximately equal to what I get when I plug 1/11 into the expansion. So 1 plus 5 over 2 lots of 1/11 minus 5/8 lots of 1/11 squared. The square root of the fraction simplifies down really nicely to the square root of 3 over 2. And when I plug 1/11 into the expansion, we get 1183 over, and that should say 968. The observant amongst you will notice that where I've written 468, that is an error. Congratulations for spotting that. Square root of 3 over 2 is the same as the square root of 6 over 4. I can split that up and call that the square root of 6 over the square root of 4. And that's equal to 1183 over a now corrected 968. And so square root of 4 is 2, so if I double both sides, the square root of 6 will be equal to 2 lots of 1183 over 968. And that comes as 1183 over 484. And that fraction is my approximation for the square root of 6. Question number 12, we have an exponential model here. From the information that is given to us, we know that 32,000 will be equal to a lots of p to the power of 4. It's 4 years after 2001. And that 50,000 will be a lots of p to the power 11. 2012 is 11 years after 2001, 2001. So we have two simultaneous equations here. A nice little trick to simplify them is to divide one by the other. There are other ways of doing it. You can make A the subject. You can try and make P the subject if you want. But if we just divide one by the other, the A's will cancel really nicely. We'll get P to the power of 7 equals a simplified 50,000 over 32,000, 25 over 16. Find the 7th root of that. On the calculator, P comes out as 1.0658 to 4 decimal places. Part 2, we can now work out A by substituting that into either of the equations. I've used the first one, so 32,000 will be A lots of our new value of P to the power of 4. So dividing both sides by 1.0658 to the power of 4, we get a calculation we can plug in to work out the value of A. Because this is a show that question, I'm going to do an extra step of writing that that's equal to 24,796, and that is approximately equal to 24,800. For BI, that A is giving us the initial value of the car. That's the value of the car at time 0, if you like. The value of the car in January 2001. And P is going to tell us the rate at which the car appreciates in value. So it's almost giving us a percentage increase per year of 6.58%. It tells us about the rate at which the car is increasing in value. And there we go. Part C, to find the year in which the value of the car exceeds 100,000, we can just do a little rearrangement. We want 100,000. We're essentially solving to find t. So 100,000 is equal to 24,800 times by 1.0658 to the power of t. You can take logs of both sides, bring your t down if you want to, or if your calculator allows you to do a log of a specific base, it's more straightforward. You can do log base of 1.0658 of 100,000 over 24,800. Comes out as 21.88, which is the year 2022. Question number 13. So this is an integration question. So I'm going to use a substitution. Putting the substitution u equals x plus 2 essentially puts the u under the square root, which is easier to integrate perhaps. Differentiating u, we get 1, so we can replace du with dx. I'm going to run the two values 0 and 2 through the substitution to get two new values, 2 and 4. I'm going to factorize the 2 outside the integral, bring it out the front. So we're now integrating, but rather than between 0 and 2, between 2 and 4. X, I'm now replacing with u minus 2. And the square root of x plus 2 is now the square root of u, or if you prefer, u to the power of a half. I can expand out that single bracket expansion, so u times u to the half is u to the 3 over 2, and minus 2 times u to the half is 2u to the half. And so we can integrate all of that with respect to u one at a time. I'm going to leave my 2 out the front just to keep us a little bit tidier. It doesn't matter if you've included 2 inside the integral, that's absolutely fine. U to the power 3 over 2, add 1 to the power, gives us 5 over 2, divide by the power is 2/5, so 2/5 u to the 5 over 2, and then subtract u to the power of a half, add 1 to a half is 3 over 2, divide by 3 over 2 is the same as timesing by 2 over 3, so that will be minus 4/3 u to the power of 3 over 2, and our two values are 4 and 2. So I'm going to substitute 4 in, and then I'm going to substitute 2 in and take the second from the first. Because to show that question, I'm just going to make a little extra effort to show the substitution of the values into the integral. And substituting the 2 in. Okay, so working each one of these out, well, 4 to the power of 5 over 2, you can do this on your calculator if you want to, or if you want to have fun with some mental gymnastics. 4 to the 5 over 2, we can square root the 4 first to get 2, raise it to the power of 5, 2 to the power of 5 is 32, 32 times 2/5 is 64/5. 4 to the 3 over 2 is going to be 4/3 times 8, which is 32 over 3. And then for the other ones, 2 to the power of 5 over 2 is going to be, we're going to have, what's it going to be, 4 times the square root of 2, so 2/5 times 4 root 2 will be 8 over 5 lots of root 2, and similarly with the second one. Then we'll simplify these fractions and surds where we can, and eventually factorize out 32 over 15, to leave us with 1 plus a half root 2. I could have just factorized out 16/15 at that point. Perhaps would have been slightly simpler, but it doesn't matter. You end up with 32/15 of 2 plus root 2, which is what the question wanted. Okay, question 14, the parametric equations question. So we're coming up with the Cartesian version of the parametric equations. The first thing I'm going to do is do a little rearrangement of the x coordinates. bring the 3 onto the left and divide by 2. So sine of t will be x minus 3 over 2. Then taking the equation for the y coordinates, so that's y equals 4 plus 2 cos 2t. And then using the trig identity, cos of 2t equals 1 minus 2 sine squared t. I'm using that one because I know I have an expression for sine t in terms of x. I could have used the other double angle formula for cos of 2t, but it would have taken longer to reach something sensible. So replacing cos 2t, 1 minus 2 sine squared t, and then substituting the sine t for x minus 3 over 2. And we now have a Cartesian equation for our curve, and we just need to tidy this up now. Okay, so I'm going to square the x minus 3 and square the 2 separately in the fraction. Gives us that fraction over 4. I can simplify that fraction down. Actually, I'm going to expand out the single bracket first. So 2 times 1 is 2, and then 2 times the 2 at the front gives me 4, lots of the x minus 3 squared over 4. And obviously the 4's will cancel. And the 4 plus 2 is 6 at the front, so we get 6 minus x minus 3 all squared, which is what the question wanted. For BI, we need to sketch the curve C, so there are my axes. We have a maximum point at 3, 6. We can read that off from the completed square form of the equation. And this is going to be a negative parabola. Now, t is between 0 and 2 pi, which means that the x-coordinates will range between 1 and 5, because sine t will vary between minus 1 and 1. So the smallest value can be when sine t is minus 1 will be 3 minus 2. And the largest value when sine of t is 1 will be 3 plus 2. So the two correct x-coordinates which restrict the domain will be 1 and 5. So I'm only going to draw the parabola between those points. You can work out the y-coordinates from substituting 1 and 5 into the completed square form of the quadratic. For BII, it asks us to explain why C does not include all the points, where x is a real number, and it's just for that reason. It's because it's going to be limited between minus 1 and 1 for the sine values within that range, or even beyond that range. That would also be true. And so x will be no smaller than 1 and no bigger than 5. For C, we know we're dealing with a line x plus y equals k. There's going to be a range of values of k where it intersects our curve C at 2 points. To help you see that, I'm actually about to draw the two lines which show those boundaries. This question is quite tricky to get your head around. We've got x plus y equals k, the gradient of that line is minus 1. And so the first thing I'm going to do is work out the point on the curve where the gradient is minus 1, at which point this line, x plus y equals k, will be tangential to the curve. So to do that, I've differentiated the curve, I've equated it to -1, and I solve that, and we get the point x equals 3.5. And you can see I've now drawn the two lines that are going to help us there. The first line on the upper right is when the curve is tangential to x equals 3.5, y equals 5.75. That allows us to find our upper bound for k. The second curve passes through the point 5,2. If the line were any more to the lower left of that, then it's only going to intersect C once. And so that gives us the lower bound for k. So the smallest value of k is going to be 7 from the 5 plus 2 in the coordinates 5, 2. And the largest value is going to be 9.25 from the sum of the x and y coordinates. Well done if you managed to get that one. Goodbye.